This episode was supposed to be a straightforward validation of our database performance plan using PgHero and PgAdmin. Up to this point, the system was running with only 100 rows in the database, which is obviously not representative. That's why I decided to add around 3 million rows and see how to read and write paths behave under more realistic conditions. At that moment, I honestly thought that I had broken the entire series. A single select count query, something that looks harmless, started dominating the entire database load. So this episode is about using PgHero and PgAdmin to understand what actually happened, why this pattern is so dangerous at scale, and how, somewhat luckily, we still managed to land with almost the same results in the end. So let's have a look on we are going to take a look into indexes for each of the catalog brand. So we have indexes on 3 columns, which we have catalog brand ID, catalog brand ID, catalog type ID, and name. And so this is how it looks. So indexes are on 3 columns: catalog brand ID, catalog type ID, and name. And now we should understand what kind of SQL we are generating. So first of all, we need to start with running the performance tests. And I have a little script which helps me with running the script. I already run it. So for the sake of it simply sends requests all the time, repeatedly to the catalog API for the same endpoint, same parameters, quick all the time, requests for the same kind of data. So let's go through the PgHero and let's go one by one and understand what's going on with the database and maybe try to tune it, and maybe we will find out any other better solutions, better options. Maybe there are any hints around that. Okay, so we have an overview, we have queries. Let's have a look here. Maybe let me click on the calls. And as we have discard all. Okay. We have select count, and it goes through entire table. So it calculates all the tables, all the rows. This is our SQL. This is our SQL, which we are calling, which entity framework is forming and then calling the npg-SQL against the database. All right, so we have the 2 queries which we're interested in. Explain. So we will paste here the query and analyze that. And pgtune, let's have a look here. pgtune, which you can fill out what kind of database you have, what kind of type, how many CPUs, how many connections, and so on. And it will generate the settings you can actually want and what's the best and the optimum way. So as you can see, max connection 300, shared buffer, this and that, right? So there's a list of things you should configure and how, and that way I was able to actually get optimal configuration for PostgreSQL. Okay, back to PgHero. So let me go to the queries. Let me go to the query which I have here, and let's paste it to the explain. Okay, guys, this is actually weird because what I was expecting is that when the cost is so high like this, with only 50 rows and the width 442, and we have a sequential scan on catalog C, which is the worst of the scans. We don't want a sequential scan going through the entire table and actually checking all of the rows. What we want is a utilization of the index. So I was expecting I would see somewhere here an index that would propose me. As you can see here, we don't see here suggested indexes. We only see one slow query. So what is going on? And I did some research with Codex, ChatGPT, etc. And it turns out that probably enough data right now in the database. What we see here, we have only like 100. Let me see. Yeah, 101 or 100 items only. So this is probably too little. The database is too tiny. So the PostgreSQL does not know what to do with this kind of data, and therefore it's proposing the sequential scan over any kind of index, and it also do not propose any kind of new indexes. So probably we should also start with adding and duplicating the data right now. I was thinking, okay, maybe we should add this kind of data later on into future episodes, because I thought this is probably one of the mistakes I've done. I should have added much more data to be based on, let's say, millions of rows instead of a really tiny database, because what we are actually testing, right? If we have so tiny database, this can be easily cached with like minimum amount of memory, and we should be operating on much higher scale. So I have generated with the AI a little script which is copying the data from the existing data, and it's duplicating that, because we want the same data probably across entire database, which will have the almost the same number of the length of this description, because it's pretty long, and we want to have the same characteristic. We don't want to have, let's say, really tiny description here, because it would influence the performance. Okay, so how it works. In here, we are specifying how many times it should be copied. So when I copy this 10 times, it's going to be 1,000 rows. When I copy this 100 times, it's going to be 10,000 rows. And I want to have 1 million, maybe have 3 million rows. So 30,000 plus 2 zeros is going to be 3 million. Okay, so it should be 3 million right now. Let me run it. Let me see if that even works. Okay, so it's running right now. Okay, we are back, and we have here insert 0, 3 million. What does it mean? Do we have it or not? Let me maybe check. Count. We remove this, and we round need this. How much do we have? Nice. Now we have over 3 million rows. 100 and 3 zeros and 3. Awesome. So we have over 3 million rows right now. And redo the performance test, the quick one probably. Guys, this is huge. That was overwhelming actually. I spent like 5 hours or 6 hours to debug what was going on with the situation. I added 3 million rows, and I thought it's going to be smooth, but it wasn't. And it turns out that realistic data, which we have added, which is 3 million and not like 100 rows, now the PostgreSQL is behaving totally different. And what was the biggest pain of that? The biggest problem of the entire situation was that we were running select count, which was going through sequentially over the entire database. And that became a bottleneck. And when we are running multiple virtual users at once, we are running it in parallel. And in our situation, we have only one CPU. And previously, we were relying on a very small size of the database, and indexes were not even accounted. They were not even needed in our database, because the database was so small that I believe that the PostgreSQL knew that it doesn't need to do any kind of indexing or scanning. It just fetches the entire data at once, and boom, it's gone. And now we had a problem because now it cannot rely on a sequential scan, which is going through the entire 3 million row, because we are running actually 100 or 200, 500 virtual user at once. And it couldn't be like that. It couldn't also retrieve instantaneously this kind of data. We had to come up with another solution, which I will say in a second. But also, what was the problem? When I added 3 million rows, def SHM, which is def shared memory, was just too small, blocking vacuums and some queries. Basically, it was that was too much, and also size of the PostgreSQL on the Kubernetes was actually too small because we added so much data. So I had to add more storage. I had to add 10 gigabytes. We only had 1 gigabyte on PVC, and yeah, Postgres had no space to work. So lesson learned: capacity, which is CPU, memory, SHM, storage. We must watch the data size, what we work on, and what kind of workload it is. And now, what's my next plan? These are two of our main queries which we operate on. And in the code, how it looks like is that we are creating two queries. It was previously only this, so required long count from entity framework, and also getting the real data and outputting this to the user. What we did right now is to get estimated catalog count. And what's the difference? Now, what we are executing is something different. Let me show you what it is. Now, we are doing this select. So we are relying on the statistics of the table. It might be a situation that is not a real value, but hence we have millions of rows and we want to get all of the data. I want to get estimated value, not like a real value, because it impacts my performance. We are relying only on the estimated value, estimated statistics of the table. So that way it is not restricting us when it comes to performance. So let's run right now the performance tests and see how it works. So the results of the reading path. So as we can see, they are a little bit worse, the results. We are oscillating from 3040 to 2434 requests per second. We could see only at one time we were a little bit better than a previous run, but this is fine. Right now we are operating on much bigger number of records in the database. So the database is not 100 rows anymore. It's now 3 million. So it's way, way more, right? And yet we could see that the median is 2,700 compared to 3,100 previously. And the maximum goes to from 3,000 to 3,200. So slightly worse. However, let's compare. Have a look on the reading response times. So right now we have a little bit more response time. We are going up to 386 milliseconds compared to the previously 305 milliseconds. So therefore we could maintain more virtual users, and we crossed in here our boundary, our threshold, and it shows us that we only had how much? Let me see. Around 800 virtual users when we crossed our threshold. Okay, let's take a look right now on the writing path. Writing path, this is also red, and we could see that it's actually slower at first. It's 2300 initially, but what I can see is and let's compare writing response times. It looks like this. This is actually the best run so far. So for writing, we are at 11:15 in here, and this is the best result so far, because the less the better, and this is the furthest run so far. It could maintain the most number of RPS and also the lowest response time. So I'm really shocked by these results. And how much we have maintained? We are at 11:15, and we maintain 800 virtual users, and we haven't did it before. So I'll note it to the spreadsheet. And a quick peek at our spreadsheet again. So to summarize that, we came up with those 4 points, and these are the results. We see that it's a slight drop on the max RPS, slight drop on the median RPS, on virtual users as well, and also on writing path. On writing path for median RPS, we see that it's more steady, we can maintain more load, and also more virtual users. So this is very good. I believe why is that? Even though we have right now 3 million rows instead of 100, I believe this is because we jumped from 32 megabytes for SHM to 256 megabytes of shared memory. So I believe this might be an explanation why we have a great results for writing path, but a little bit lower for reading path. And yeah, thanks for watching. I do hope you also learned something. If you enjoyed this kind of video, this episode, the new way of how I'm conducting this, please do let me know, and subscribe if you liked it. So see you next time.